subsort. Okay. So given an array of numbers, which is sorted, not sorted, partially sorted, doesn't matter what it is. The goal is for you is to find out the minimum elements in it within this thing, which I need to just, if I can sort only that set of elements, the entire array is sorted. That's what I want to find out. Okay? So given, let me take an example, 1, 2, say 3, and then I say 8 and 9. So I'm going to take like 4, 5, 6, 7, right? So I'm going to say 7, 6, 4, and 5. Okay? So if I sort just these things, right? I don't have to sort the whole array. I just have to sort these elements. If I sort them, it gets sorted. How do you figure this out? Anyone who has not attempted this problem, I want to just see if you can attempt it fresh. How do you find out where to begin sorting and where to end sorting? I mean, theoretically, you could sort all the way, right? It works.
Well, we look up which is already sorted on the both sides, and see the rest of it is probably that needs to be sorted. And within the
so how do I? So why don't you walk me through finding the left extent? So he's saying that clearly some part of this array is sorted from the left hand side, and some part of this array is sorted from the right hand side. Why don't we find out what that some part is, and then figure out, right?
Yeah, even then within that we don't know if it's. Are we told that all the unique elements they're going to be?
It is. It's always the case, right? I mean, you can. The answer might be you have to do all of it,
Okay.
right? But it is not. So the question here was, the thing was, he's saying, can we find out what is sorted? Is 1 sorted?
Yes.
Absolutely. So 1 element, right? Is 1 and 2 sorted?
Yes.
Yes.
1, 2, and 3 sorted?
Yes.
Yes.
1, 2, and 3, 7 sorted?
Yes.
Yes.
So that's your sorted list, right? Let's go from the right. Is 8 sorted? Is 9 sorted?
Yeah.
8 sorted?
Yes.
5 sorted?
Yeah.
Yes.
4 sorted?
Yes.
6 sorted?
No.
No.
So I stopped here. So
So
something is broken. Now
so
what do we do?
Yeah.
what we have to do is that whatever the middle section is there, find out the max and mean number. Maybe only mean, mean and max, and then whatever the section we saying that sorted section for the left side, remove all the element that is below the minimum number. So include that. So in this case 6, right? So include one. I mean anything that is greater than 7 include into the middle element. So now 7 and 6 will be middle element, and then
Greater than 7, why?
no. So we figured out this 2 section, right? That is already sorted from both directions. Now whatever the remaining middle section that we saying that we have to figure out. Within that section, find the minimum number, and then from the
So from this, right?
from this section
I have
find the
found.
minimum
So
number.
let's assume that this happened to be 5.
5,
And
okay.
this happened to be 6, right?
Okay. Yes.
Okay, if this were to be the case,
Uh-huh.
then what you're saying is that I go find the element in middle,
Yeah.
and I'm going to say this is 3 and this is 4, just so that we can continue. Same, the
Yeah.
equation does not change. Okay.
Yeah.
So now I'm saying find all the numbers that are greater than 5 to the left of 5. Is that what I'm hearing?
No. So that
The
section-
smallest element. So this could have been like 5 and maybe few other numbers here.
Yeah.
If it was that,
Yeah. So find the minimum number from that section.
so let me do 5 and say let me add 2 here, 0 and 1. Okay.
If you have 2, that other one definitely will change.
What? Oh, the
Right side, yeah. 3 and 2. Yeah.
Thank
makes
you.
sense. Yeah.
That was helpful. Okay, so I've done this. So now I have the middle element I found. So I sorted down, found this. I got the middle element. Now what I'm saying is in this list, right? What is the smallest element?
3.
3. So now I have to expand this
Yes.
till I find the point where all the numbers are greater than 3.
Right.
Okay? And then what do I need to do? Expand it all the way to the right
Less than
till I find all the
maximum.
numbers that are less than 5.
Yeah.
But then again we have to keep doing it.
Why?
Because now
That's it.
Yeah.
see
We found the
here
start and the
if
end
0, 1 and 2 is there in the left side.
Uh-huh.
Or say right
Uh-huh.
here. No, left side section 0, 1 2, yeah, and here 1, yes.
Uh-huh.
Now we have to still expand it, right?
You see
Because
that,
the
right? I did
yeah.
this. Am I done?
No, you have to keep doing it. You're
Is
not-
there a way you can do it smarter?
Okay.
Can you do it in one shot?
I see.
You can, right? Why are you actually finding the smallest number in this middle section? Why not find the smallest number
Oh yeah.
to the right entirely?
Yes, makes sense.
And so from this cut point that you have,
Right.
find the
Yeah.
smallest number to the right of it. From this cut point you have, find the
Biggest number. No, smallest. Smallest.
The largest.
no, you're finding the smallest number to the right of it so that way you can go back.
Right.
And then you're finding the largest number on this
Yeah,
side
right.
so that you can go that way.
Yeah.
How far do I have to go, right? I need to draw the cut line because that's all numbers
Yes,
are greater than
yes.
7.
Makes-
Correct?
Yeah.
That's all you need to do. That's a
Yeah, yeah.
that's a trick. Okay. So take a step back. The algorithm. So the question is, how did you even get to this algorithm? So let's actually. So let me explain the algo first, and then talk about the evolution of the algo. Right. So the thing you're trying to do is you're trying to find, as long as it's ascending, I keep going, I find the stop point. Okay. As long as this is descending, I keep going, I find the stop point. So this is my step 1. This is my step 2. Okay. Then what I've done is, now after this step, after this point, I'm trying to find the smallest number that is on this half of the equation, and I'm trying to find the largest number that is beyond this line. Done, right? Then what I've done is, now I have, since I found the smallest number on this side, I am trying to make sure that I move this back so that this, all these numbers are less than the smallest number that I found.
Yeah.
And I move this back so that all the numbers on this side is actually greater than the largest number that I found. And that's all we're trying to do. It's a very, now that you talk about the algorithm, it's so simplistic. Let's go figure it out, right? So this question is like super simple to code, but it's super hard to figure out how to get to this. How did you figure this out? How did you get to this? Without looking at the answer, how would you solve this? So the first part of it is very obvious, right? The first part of it is that you have a way of actually, you need to find the middle section that needs sorting. That is the first part. So we know that some part of, as you said, some part of it sorted, some part of it sorted. Let's find that equation, and you are guaranteed to find, you're guaranteed to overshoot your point of return, anyways, because as you overshoot, only that, because you know that these numbers have to move up, and this 5 and 3 and 1 and 4 have to come here. So you know that. So you're going to overshoot, and that should be like a 30-second check for you, and you would have known already that just sorting, just coming over there to figure out sorted is not enough. Done with that, what's the next step? Next step is to figure out like how much do I need to backtrack it by, and how do you figure out how much to backtrack by? Is that find the smallest. So from this point, you know that every number is larger anyways, because that's how you figured out, right? So since it's sorted, now you have to find the smallest number in the rest of the space. So you could potentially go through like an optimization phase here and say, I'm going to only look in the middle pile. But then very soon you discover that the middle pile is not enough. Because if you don't in the middle pile, you'll miss this one, right? And that's not enough. So that, and then the answer was like, I need to keep expanding, keep doing it multiple times in iterative. But then at the end of the day, if you just use the whole thing, you're good. And that makes it, like, it's a quick call for you to make. Once you're done with it, you got this. And once you're done with this, it's fine. One element of it is that how do you find this cut line? Once I know that the smallest number on this side is 1, okay? How do I find this cut line?
You do like a binary search.
Backtracking.
Why back? There's no backtracking here, right?
No, we can do binary.
So you know that this array is sorted,
Yeah.
okay? All you need to do is to find out the point at which the number is like, all numbers are greater on the left and right, and all numbers are small on the left. So sorted number, find the insertion point, binary search, straightforward. So these things need to click. So in one of our upcoming sessions, the initial entry, when we talk about it, I will ask you to write binary search. Given a number, I want you to write both the reduced scope of binary search and the expanding scope binary search. We'll do both, right? So that will be a writing exercise that we'll do. So, but anyway, very simple question if you know what you're doing. and it's pretty difficult to figure out otherwise. This would be the methodology that I would use. Does it make a difference if the numbers are duplicate?
What was the question again?
If you have duplicates, does that make a difference?
No.
It, no, it doesn't make a difference. Only thing is that when we suppose we found the minimum on the right side, it doesn't make a difference.
Can I rewrite this? Let me rewrite the steps so that I can. Okay. Find the drop from left. So I'm saying it's 0, it's 2, it's 6, it's 7, and it's 5, right? This is the drop. So I will get, this is 0, 1, 2, 3. So I will get, I got I equals 3. Or rather, I got I equals 4 because that's the start of the drop. Okay? Then second thing is find the lift from right. So we said 3, 1, 4, 8, 9, right? So we got this line. So I got the index of this, which is for this. Okay? Then what did I do? Step 3 is find like the point. I'm going to call this A, I'm going to call this B. I'm going to find the point, find smallest number that is greater than right of A, right? That's what we did. Then what I'm doing is fourth step is I'm saying find index C such that A of 0 dot 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 C, all of them are less than A, right? So less than, okay? That's what I've done. And 4, 5 and 6 are the equivalent things on the right. Will this algorithm change if I actually change the numbers, if I were to say that they are duplicates? First, any questions with the algorithm? Whatever I kind of verbally said earlier is what I've written it down. So I don't think I've changed. I don't think I've changed it. Any questions? You want me to add duplicates just to figure out?
So duplicate, either it can be in one of the section or in middle, and I don't think so it makes any difference because we are finding.
Okay. Where is the insert point? So what is the index?
It will be
What is the index C?
the index of 0.
Which is wrong.
1, right?
Which is wrong.
Okay, less than equal to.
Right? That's the difference. Because I want this to be the cut line.
Yeah.
Because I don't want to sort this. Because then if I sort all of these things, then one will come here and I'll be good. Right? That's what I'm looking at. So this is the difference.
Yeah.
Okay? Does that make sense for duplicates? So if you have duplicate elements, then some of the duplicates will already be in the right place, right? And some of the duplicates might be requiring to be sorted. So now, if you draw your cut line to the left of all the ones that are in the right place, then you will be unnecessarily sorting those things. You don't have to. So by drawing the cut line towards the right of that, so that is why it's less than equals is important. If you just do less than, then you will be drawing it to the left of the cut line, the left of the equal elements. You want it to be drawing that cut line at the right of the equal elements so that you can so that when sorted, the smallest element will anyway form the leftmost extreme, and it will just get joined. It will be fine. Take a few examples. Like take this example, walk it through. You'll probably see the difference. So that's why the less than equals. That is what is the crux of it. Okay. What about negative numbers? Does that make a difference? If I have negative numbers, does that make a difference?
No.
What if all the numbers are negative? Does that make a difference?
No.
Sure.
Yeah.
Need to be more confident.
Yes.
Yes, absolutely.
No,
Right?
it doesn't make difference because you can always.
The numbers, they're just relative. You're only doing comparisons. You're not doing any funky math. So if you had been doing additions, what would be my next question? Let's assume you're doing some kind of like weird additions and trying to figure out something. What would be my question?
Negative and positive.
Negative numbers, is there a problem with addition?
Negative.
Really shouldn't matter. What else?
Overflows maybe.
Overflows is a challenge. In the previous question, how did you find the midpoint of a line segment? How did you figure out where is the center of the circle, right? That was a square. How did you figure that out?
I guess add two numbers and then divide by 2.
What if
It overflows.
it overflows? What do you do?
We should always divide and add.
Subtract it.
If you divide and add, then it's integer. So what do you do?
Yeah.
So you subtract and then take the offset.
Yeah.
That's it.
Oh, yes. That's it.
So what you need to do? So how do you find? So if you look at the merge sort code, I believe in merge sort or quick sort. Merge sort code in Java had a bug till 2016 or 2017, where they actually were trying. How do you find the midpoint?
Yeah.
Right, to do the merge sort. So they were actually doing the fix was essentially mid equals high plus low by 2 was actually changed to mid equals low plus high minus low by 2.
Yeah.
What's the difference between the two?
It can overflow H plus L, but in the
Second way it cannot overflow.
Yeah.
Only a problem for sufficiently large numbers and all that stuff, which was not an issue back in those days, but started becoming an issue. So always remember that. I should have brought this up when we did that earlier, but so these are all the things that you want to keep in mind, and these are all the things that actually make a difference in your interviews when you're actually answering, and these are all the key pointers that you want to address as you go through the thing. You're saying, oh yeah, that might overflow. Let me actually fix it, or let me just write it the right way so that it actually fixes it. And those things will definitely earn you brownie points. I mean, if it's naturally coming to you, then that's good. Don't have to retrofit it, but there are like dozens of these minor rules, like null checks, overflow checks, and like negative checks and things like those. Does it make a difference if this array is like gigantic? What if this array has like hundreds of thousands of elements? Would that make a difference? No? Is it possible for this array to actually have the unsorted thing to be the whole array itself?
It is possible.
Yeah.
It is possible, right?
Yeah, it's possible.
Okay. At what point of time will you detect that? 1, 2.
Both point 4 and 6.
Will you detect at 1? Find a drop from the left. Will you detect at 1?
Yeah.
In a
Zero.
one kind of.
Yeah, it will be the first element from the left.
Yeah, I mean we can detect if it is starting from left at the point 1.
You will not be able to detect that because you will assume the first element is sorted.
Yeah, so
The second.
but then the moment you go second, you know that at least
Yeah, if it is.
now.
No, 4 will only tell you that the cut line is wrong. 1 will tell you. So if you had like something that's perfectly unsorted, right? Right?
Yeah.
Your 1 will say this is it. My cut line is
That's
here.
it, yeah.
Okay, yeah.
My 2 will tell me that my cut line is here.
Yeah.
And my 3 and 4 will tell me no, it's not here. It's actually here.
Yeah. So 4 and 6 will.
So
tell the
4
right.
and 6 are the ones that will tell you where the correct cut line is. At no point of time will 1 and tell you give you the correct cut line. There's no chance, right? Unless the array is like empty, which is the only case we can think of where the cut line is exactly nothing.
But how do you infer if the cut lines are in the first and the last elements, it's not sorted?
How do you know that? What if this was 1 and this was 9? You don't have enough information to, the cut lines will still be drawn the same way. except that the 4 will cannot push this any further. Because all the elements to the right of this line are all greater than this 1, so you're golden. There's nothing, or equal or greater than this line, right? You're golden. So you will not know the cut line. You'll start with this cut line. That's a drop point and the lift off point. You will figure out, but good chance that they are not the cut lines. I mean, they may be, but they may not be. In fact, they won't be, because if it's this way, the cut line will be here. There is practically no chance that you will figure this out unless the array itself is sorted. So you've gone all the way to the end of the array and you've figured out that it's there. The fact that there is nothing required is probably the example that will help you answer here. Otherwise, invariably you will go 1 over.
1 over.
At the minimum you have to go 1 over. Otherwise, if the element of unsortedness is there, then you'll always go 1 over. Right? So the cut line will never be, will always be wrong, except for the case of where there is a sorted. Okay. So these are the points that I think these are the different sets of elements. I know it's been a little haphazard today. I wasn't super organized for today's session, so we're just walking through different points as they arrive. Any questions on these?